Chapters 19 and 20 are going to take a look at electric current and the resistance in electric current. So let's start out by defining current. Current we're going to define as the rate of charge flowed. Another way to look at current is the cross-section of charge flow per second. The symbol we're going to use for current is I. The equation for current is current equals charge over change in time. Units are amps, so an amp equals a coulomb per second. Current is actually moving charge. Electrons are the charge that move because protons are locked in the nucleus. When we talk about conventional current, we talk about current as described in this country. And current is described in this country as the flow of positive charge. That's counter to what is actually happening, but let's take a look and see why that might make a little bit of sense. So if we look at this diagram here, we have electrons flowing from negative to positive. What we would say is that the electrons are moving from left to right. We would talk about the current moving from right to left, from positive to negative. So here would be an example of electric fluid flow, or the current, where we have a flow of positive charge. This isn't what's happening, but this is how we describe current. If we take a look at this diagram where we have currently positive charge and a negative charge in each atom, we have the electrons moving from left to right. We see that the positive red hole moves from right to left. So again, electrons move from left to right. So in some sense, we can talk about current as a flow of positive holes where electrons used to be. When we have a complete circuit, the electric field is set up in the conductor, and the electric field travels close to 3.0 times 10 to the 8th meters per second along the conductor. If we remember from previous units, 3.0 times 10 to the 8th meters per second is the speed at which electromagnetic radiation travels through space and somewhat through the atmosphere. So the electric field travels through the conductor at about that speed, but the field moves faster than the electrons. The electrons don't travel that fast. The electron's path isn't direct, and they collide with other atoms, and they're making continual path changes. They don't travel in a straight line. So what we can take a look at now is something called drift velocity. Drift velocity is the net speed with which an electron moves from one end of the conductor to another. What we have here is a picture of electrons in a current. The little moving dots are the electrons. The large dots are the nuclei of the atoms. So the electrons are moving around the nuclei. As we change the current, as we increase it, we'll see that we make the electrons move faster, and we can make the light glow brighter. Now we see red dots, little red dots, along with the little yellow dots. The little yellow dots are the electrons that are pretty much stuck to the atom. The red dots are the electrons moving through the wire as the current flows through the wire. And we can see, if we try and follow one of them, that they don't follow a straight path. They play bumper cars from one atom to another. The faster the current, the more the light glows. So here we have a few electrons traveling from left to right. We can especially see them along the bottom edge. Now we have more electrons moving as the current flows. Current is flowing, in this case, from right to left. The electrons are moving from left to right. We're going to deal with two kinds of current, primarily with the direct current, first of all. Direct current is usually referred to as DC, in which the current is moving in only one direction in the conductor. And most batteries that we work with, most batteries that power our electronic devices, supply direct current. The power supplies that we're going to use when we build circuits are DC, or direct current power supplies. Alternating current is the type of current in most buildings, houses, businesses. Alternating current is constantly switching direction within the conductor, and it does so at a particular frequency. It is referred to as AC current. In the United States, the frequency of this alternating back and forth is 60 hertz, or 60 cycles back and forth within this conductor per second. When electrons travel through a conductor, they are continually colliding with metal atoms, and this slows them down on their journey. As they slow down, they lose energy due to all these collisions. We learned in collisions and in momentum that inelastic collisions do not conserve mechanical energy. That's what we're seeing with these electrons. This slowing down due to collisions of electrons with the atoms is described as the resistance of a conductor. There are a variety of things that can affect the resistance of a conductor. One of the things that can affect the resistance of a conductor is how long the conductor is. The longer the conductor, the more resistance it can generate, which makes sense because there are more metal atoms that the electron can collide with, the longer it has to travel through a conductor, and so the more resistance it will have. Cross-sectional area, actually the bigger the cross-sectional area, the less resistance something has. So if I have a long distance that something needs to be carried, if I can have a big diameter wire, then it's going to have a lower resistance than a skinnier diameter wire. Various metals have more or less resistance than others. Copper, silver, and gold are the three metals that have the lowest resistance. Aluminum is used in some construction as wire, has a higher resistance. So what that means is aluminum wire, as it is used to carry current, is going to warm up more quickly than copper, silver, or gold. Gold is actually the best conductor of electrons, but it's pretty expensive, so copper is used because it's one of the top three. Another thing that affects the resistance of a conductor is its temperature. The higher the temperature, the more resistance there is. We learned in the thermodynamics unit that kinetic energy of particles is tied to their temperature. So the higher the temperature, more kinetic energy they have, which means those metal atoms are going to be jiggling around in space, so they're going to be larger targets for those electrons to run into as they're trying to get from one end of the wire to the other. So the cooler the wire, the less resistance it has. For some conductors, below a critical temperature defined by the material, the resistance of a conductor can drop to zero. When I have a conductor that has zero resistance, we refer to it as a superconductor. So superconductors, as some of those found in mass spectrometers, are run at liquid helium temperature, which is 4 degrees Kelvin, because the resistance in those conductors is zero, and so you lose zero energy as you're running the current through the wires. Here we have an example of a number of different types of resistors, and the color coding helps us to identify what the value of the resistor is. Color code is listed in the box, and it's rainbow oriented, which is helpful because if you know the order of the colors in the rainbow, you can figure out what the number of each one represents. So we start with black and brown, and then we go through the rainbow colors: red, orange, yellow, green, blue, violet, and then we still need more colors, so then they go to gray and white. Each color represents a number. When we're looking at resistors, the colored bands always start closest to one end. The first band gives the first digit, the second band gives the second digit in a 2-digit number, the third band gives the power of 10, and the fourth band gives us the percent tolerance. So if we take a look at this, we have green. Green is 5. Blue is 6, so this is 56 times. And then we have yellow. Yellow is 4. So it's 56 times 10 to the 4. And the units for resistance are ohms. It's an omega. So that's the resistance of that resistor. And it's a gold band, so its tolerance is 5%. So for the second resistor, we have green, which is 5, brown, which is 1, black, so it's 10 to the 0 ohms, and the gold is a percent tolerance, so it's plus or minus 5%. So for this case, we have a 51 ohm resistor plus or minus 5%. So that means that 51 minus 5 We can go down to 46 ohms and it still will meet factory specs, or we can go up to 56 ohms and it's still within factory specs. So when we're building a circuit and we need resistors, we're going to keep the colors and use the colors to help us figure out what resistors we need to add in our circuit.